Hello everyone, I am Sujata Singh, Faculty of Chemistry. I welcome you all to an official YouTube of SRN International School. In this video, I am going to discuss the topic, the solid state for grade 12. So let's begin with the topic. Let's study about the general characteristics of solid state. Solid state have definite shape, mass and volume. Its constituent particles have fixed position and can oscillate about their mean position. Intermolecular distances are very small and intermolecular forces are strong. They are incompressible and rigid. Classification of solids. Solids are classified as crystalline and amorphous. Crystalline solids have definite geometrical shape, whereas amorphous solids have irregular shape. Crystalline solids are long-range order, which means that pattern of arrangement of particles are regular and they are repeated periodically over the entire crystal. In the case of amorphous, they are short-range order, where the pattern of arrangement of particles which are periodically repeated is only for short distances. Crystalline solids are anisotropic in nature, which means that physical properties like electrical resistance, refractive index, they have different values when measured along different directions. Whereas amorphous solids, they are isotropic in nature. Here the physical properties have same values when measured along different directions. Crystalline solids are true solids, whereas amorphous solids are pseudo-solids or supercooled liquid. For example, glass panes which are fixed to windows of old buildings, they are found to be thicker at the bottom. And this is because of the reason that the glass which is amorphous, it has a fluidity, that means it flows very slowly and becomes thicker at the bottom. So the examples are like quartz, which is a crystal quartz, which is crystalline in nature, and the quartz glass is amorphous in nature. Other examples of amorphous are like rubber and plastic. Crystal lattice. Crystal lattice are regular three-dimensional arrangement of points in space. The characteristic properties seen for the crystal lattice are: first, these points in space are known as lattice points or lattice sites. Second, lattice points represent atom, molecules or ions. Third, lattice points are joined by straight lines to bring out the geometry of the lattice. Unit cell. Unit cell is the smallest portion of crystal lattice which, when repeated in different directions, generates the entire lattice. It is characterized by three edges which are denoted as A, B and C, and three angles. These three angles are alpha, beta, gamma. The angle between A and B is taken as gamma, between B and C is taken as alpha, and between C and A is taken as beta. So the 6 parameters of the unit cell are given by 3 edges and 3 angles, that is A, B, C and alpha, beta and gamma. Categories of unit cell. There are two categories. First is primitive unit cell or simple cubic unit cell, and second is centered unit cell. Primitive unit cell or simple cubic unit cell has the lattice points or the particles present in the 8 corners of the cube, whereas centered unit cell have the lattice points or the particles present at the 8 corners as well as the other position of the cubic unit cell. Centered unit cell is again classified as body-centered cubic unit cell (BCC), face-centered cubic unit cell (FCC), and end-centered cubic unit cell (ECC). Body-centered cubic unit cell has 8 lattice points present at the 8 corner along with the 1 lattice point present at the center, which is called as body center. In the face-centered cubic unit cell, it has 6 lattice points or the particles present at the 6 faces besides the 8 lattice points present at the 8 corners. In the end-centered cubic unit cell, it has 8 lattice points at the 8 corners of the cube, and also it has 2 lattice points present at any of the opposite face of the cube. Number of atoms in a unit cell. It is denoted by Z. In a simple cubic unit cell, since there are 8 atoms present in the 8 corners of a cubic unit cell, and each of the atom contributes 1/8 of its part inside the unit cell, so therefore the total number of atoms in the simple cubic unit cell will come out to be 1. In the BCC, that is body-centered cubic unit cell, the 8 atoms present in the 8 corner will contribute 1 atom, that is 1/8 of the 8 atoms. And 1 atom is already present in the body center, so this comes out to be 2. So the total number of atoms that BCC have is 2. In the face-centered cubic unit cell, that is FCC, again the 8 atoms which are present in the 8 corners will contribute 1 atom, since 1/8 of that atom multiplied by 8 atoms gives out to be 1 atom. Now the 6 atoms which are present in the 6 faces, so each of the atom in a face will contribute half atom inside the unit cell. So since 6 atoms are present in the faces, so half multiplied by 6 gives out 3 atoms. So total number of atom in this phase FCC would be 4. The three-dimensional view showing the number of atoms per unit cell is seen as in simple cubic unit cell it will be 1. In face-centered cubic unit cell it will be 4 atoms, and in body-centered cubic unit cell it is 2 atoms. So Z equals to 1 for simple cubic, Z equals to 4 for face-centered, and Z equals to 2 for body-centered. Close packed structures. In this, the lattice points, which represents atoms, molecules, or ions, they are all closely packed to give the entire crystal lattice. So there are 3 types: close packing in 1 dimension, when these spheres are arranged in 1 row. Second is close packing in 2 dimensions, which are of 2 types: square close packing and hexagonal close packing. And third is close packing in 3 dimensions, which are again of 2 types: hexagonal close packing, that is HCP, and cubic close packing, that is CCP. As shown in figure, the hexagonal close packing in 3 dimension is having a central sphere surrounded by 6 spheres, and when the 6 spheres are joined together, it gives a hexagonal shape. Therefore, it is an HCP, that is hexagonal close packing. In cubic close packing, which is CCP, when its unit cell is taken, then its unit cell comes out to be FCC, that is face-centered cubic unit cell. Packing efficiency is the total percentage of the space filled by the particles. Packing efficiency in FCC is 74%, in BCC it is 68%, and simple cubic it is 52.4%. It is calculated by using the formula volume of the total number of atoms divided by volume of unit cell multiplied by 100. So lastly we come to the density of unit cell. Density of unit cell is given by mass of unit cell upon volume of unit cell. Since unit cell is cubed, so therefore the volume of unit cell is taken as A cubed, where A is the edge length of the unit cell. Mass of unit cell is given as molar mass of the atom divided by Avogadro constant Na. And Z is the number of unit cells. So depending upon which unit cell we are considering, so we'll put the value of Z. So mass of unit cell comes out to be Z into M, where M is the molar mass and Na is the Avogadro constant. So density of unit cell is equal to Z multiplied by M upon Na multiplied by A cubed. Dear students, I hope you must have understood this topic. Keep learning, keep exploring. Thanks for watching. Please like, share, and subscribe to our channel for more informative videos. Namaskar.